I'd like to welcome you to Sergei's talk.
Yeah, thank you very much for the introduction, and very glad to be here.
Thank you much for joining us.
Yeah, thanks everyone for coming to my talk. So this is going to be a very high-level overview of data modeling and data processing techniques. I will basically try to compress down to 20 minutes several decades of evolutions of techniques in that space, and also take a quick peek into the future. So the focus is going to be on really telling you about the key trends and in a very simple language, and also showing you the pitfalls and dead ends that some of those trends can end up in, and really build a common vocabulary between people with very different backgrounds and data. So as you heard from my background, I've been on both sides of the enterprise data. I've been a software engineer and also on the analytics side and data engineering. And what I've seen that despite data being something that connects these two camps, the entire understanding of what data is seems to be very different on both sides. And this seems to be resulting in a lot of tensions and inefficiencies. And I discovered that modeling time and modeling how things change over time seems to be at the center of this problem. So we're going to look at those two camps from at data from both of these perspectives. And we're going to start with OLTP. So OLTP, this is usually the source of the data in the company. This is your application, your service, or your product that you're giving to the clients, something that creates external value for them. If we ask a software engineer to implement a simple marketplace service for an online video game, let's say, something that to sell hats, for example, right? It doesn't really matter for this example. This is what the results might look like. So we'll have SKU with some prices attached to them. Every SKU might have one to several items, and users are going to have accounts, and they will have some currency balances, and they're going to have inventory. What I want to highlight here is that this is the default. So if you, no matter which engineer you ask this, from junior to senior, a vast majority are going to come up with this exact solution, because this is how we taught to view data. This is coming straight from our school books, straight from our database courses. This model is, of course, non-temporal because there is no time in this model at all. It models the current state. So there is no time, there's only state transitions that happen through CRUD queries. So if we deploy this application and run it in production, we're going to start wondering what it's actually doing, like what is actually it performing. If we ask simple questions like what it takes, how long it takes for a user to acquire most of the content in our game, this is not something that we can easily answer with this database model. So this is when we discover that state is actually not as interesting as dynamics of change. And analytics is all about time, the dimension that we decided specifically to ignore. And this puts engineers on a long and windy path of introducing time back into the data somehow, and they invented a lot of ways to do so. So first two ways are really just stopgap solutions. Engineers might not have a lot of time for analytics when they launch the application. So they may say that, oh, we capture database backups every day, so why don't you use just those? So this is, of course, a horrible, very low frequency source of data. You need to diff them together, and it's lossy. You will not be able to reconstruct any transactions from these backups. The second solution, change value selection, is just iteration on those, where we take incremental backups. We push the frequency from one day, let's say, to every half an hour, but it's still lossy. You will not see transactions here. So this brings us to a big contender, right? Change data capture that you probably all heard of. It assumes that for every state table in the production database, we have a log table that contains every single change that happened to the state table. And we capture this change either by triggers or from replication logs. So from engineer perspective, this is a pretty cool solution. They might say, we achieved the ultimate granularity. It's lossless, it's transactional. But analysts might not be as pleased with it, because what they have to deal with is this, this is something, what I call what happened game. They look at these log tables, and what they see is that in time T1, there seems to be a change in account balance. It dropped by 100. And they see that an item was added to the user's inventory. So for looking from SKUs, they might infer that this probably was a purchase transaction that happened. So really, you don't want to be in this position. What's happening here is information loss, because what state changed doesn't really tell us why it changed. Such state changes are what we call anemic. We're seeing the numbers changing, but we don't know what happened from the business perspective. So you don't want to be in this position of reconstructing what happened. Like your application is already doing this hard work of translating business transactions into state changes to record them in database. If you're going to be using state changes for analytics, you will be basically creating this mirror copy of your entire business logic on the analytics side. So definitely not something you want to do. So I think CDC really works on a wrong level, on the level where information has already been lost. And it's surprising to me that it keeps re-emerging in all the data processing technologies and often being advertised as the best solution to extract data from the prod databases. Because really, I think it might work in very few narrow cases, but it's not a good general case solution. I think the best solution in this case is not to lose information to begin with. So this is what happens in domain events, which is a step in the right direction. Application still maintains its state in a database, but in addition, we have an event log table where we capture business events. So the data that we capture actually speaks the language of our business. So the entire previous example here can be captured as a single event, SKU purchased, that contains very detailed descriptive information of what happened. This solution might be pretty hard to maintain from the engineering perspective because in the application, you end up with this duality between state and events. So engineers might not be as happy with it as analysts. So this brings us to event sourcing, which flips the entire problem on its head. Instead of storing state, we store only history in a database, and we reconstruct the state on demand from the events. So having events like deposit for 1,000 currency and a purchase for 100, we can easily tell that the current account balance is 900, right? It's pretty simple projection operation. State might still be stored in a database, but it's only used for optimization for queries. So here the projector component might sit and listen to all of the history that is happening, that is written to the event store, and continuously update the state in a projection database. Extracting data from event store into data warehouse really becomes a super simple operation because data is already in the form of historical events. It's ready to be processed. So I really do believe that there's such a thing as good data, and it's the data that speaks the language of your business. You should learn to recognize and avoid anemic models. State projection really is just state is just a projection of history. It has information loss by definition. So it's not fit to be your primary data model. And I think the defaults are obsolete. Like, why is it okay for us to lose history or do destructive updates as the first implementation? I really believe that something has to change in the way we teach data to young engineers, because analytics really is a core requirement, not something we can bolt on later. So what's going on the analytics side in the meanwhile? So OLAP is, it's analytics. It's focused on providing internal value to the business, usually providing insights that drive optimizations and that drive strategic planning. And for a very long time, Star or Snowflake schema was the classic implementation of data warehouse, or also known as OLAP cube or pivot table, that allows you to slice, dice, and drill down and up in your data. And it's said to be really great if you have clean and well-structured data. At the center of it is the fact table that just records the events over time. So here we have transaction happening at T1, T2, T3, etc. This is a very dense table. It's optimized for high rate and high volume of data. And most columns are foreign keys to the dimension tables. Dimension tables, also known as slowly changing dimensions, have several different forms, but the most common one I've seen is the one that uses validity time intervals to capture change. So here we have a SKU1 that had price 100 from time T1 to T2, and then at T2, the price had been dropped to 50. So it's been said that the SCDs are great for data that changes infrequently, but you might ask yourself, how frequent is infrequent? In our online game where prices change once a week, let's say, it doesn't sound so frequent to me. But if we were implementing data warehouse for Costco or for Walmart, where prices can change hourly on thousands of SKUs at a time, that sounds pretty frequent, right? Also, what's the reason for the change in this case in the SKU price? Why did the price drop? Was it a promotion? Was the expiration date coming up or something else? So this brings us again to this problem of anemic data. Whether it's a problem for you, it really depends on your use case and on your business. And the Snowflake schema really has to match closely your business needs, because the way you design it, the way you architect it, depends on the questions that you're going to be using it to answer. So you kind of have to know all the questions and anticipate all the questions up front, which is pretty hard to do. And in reality, you probably will not. So this, in combination with Snowflake schema being really hard to evolve, kind of caused its downfall and the gradual transition and rise towards ELT and data lakes. So extract load transform has a very simple idea. We grab the data from the application and store it in the raw form with very minimal processing. And then we use massive parallelism to scan this data and analyze it on demand. So it's really interesting. This concept becomes with combination with event sourcing, because in event sourcing, our data is already in the form of historical events. If we apply ELT to it, data lakes are just becoming a very big event stores. They just store all the history of all applications, right? So this is a great indication to me that OLTP and OLAP data models are actually converging. Temporality manifests itself not only in how we model data, but also in how we process it. And I think this aspect is significantly less understood. So let's look at the batch processing first. You're all familiar with batch, I'm sure, because you do batch processing when you use Excel, you do batch processing when you query database through SQL, you do it when you write your scripts in Pandas or R. Batch treats data as a bounded list of records. So I'm going to switch up the example and raise the stakes a little bit and say, let's analyze and calculate the daily number of COVID-19 cases using a data set of hospital admission records. So let's kind of try to recreate the statistics that you're getting from the news daily today. We're going to do it from using a very simple SQL query, right? We're doing a group by of all the cases based on date, and we just count the numbers of cases in every bucket. So by running this query every midnight, we can expect to get statistics that we want. And we're going to look at this from using bitemporal diagrams. So don't panic, they're actually really simple. On the x-axis, what you see is the event time. So this corresponds to the time when some event happened in the real world. So on Thursday, for example, we have 2 registered COVID-19 cases. On the y-axis, we have system time. This tells us when the event entered our system or entered our database. So in ideal case, we can imagine that as soon as event happens in the real world, it immediately gets into the database. So this is what creates the zero delay propagation. And this is what gives us this very nice diagonal. So let's see how batch performs as this in this idealized case. Remember that we're running the query every midnight. So on Thursday, we run it and it gives us 2. On Friday, we run it, it gives us 1, but also 2 because we just rerun the entire batch query on the entire data set, right? And so on. So this is looking pretty well. There's some redundancy going on here, of course, but it's not a big deal, right? Unfortunately, in reality, this is not at all how data looks like. Because data can be late, it can be out of order, it can be lost and then backfilled, or it can be wrong and then corrected later. So, for example, I live in British Columbia, and our CDC does not publish any data on COVID-19 cases on weekends, for example, for some reason. This is what creates this big gap in the middle. And hospitals might enter data on night shifts on the next day. So on Thursday, our event might actually be entered on Friday. So if we apply batch to this type of data, on Thursday we get 1 instead of 2. On Friday we'll get 0, and so on. So we're getting a lot of wrong results, especially on weekends. But what's worse, we're also rewriting the history. So someone comes to us complaining about the 0 that we got on Friday. The next day, we're gonna say like, what 0? The 0 does not exist. We just replaced it with 1, and there's no record of it left anymore. So batch processing, using batch processing on event data really is non-reproducible, because as results, your results are going to be changing as new data arrives. And the corrections that you're making are not explicit. Nobody's going to know that they happened. What's worse, the errors that we're seeing are mostly concentrated in recent results. And this is the results that everyone cares about the most, right? If you plot the graph of COVID-19 cases based on the results we just got, we're going to see this downward trend in our graph that is always going to be there on every day. And if you're like me, you're probably already learned from using like all the dashboard tools to ignore this downward trend. But I cannot honestly say that it doesn't affect me. Like when I see the error graph like that, I keep always thinking like, oh, maybe they are going down, maybe it's getting better. So I think now imagine that politician looks at this graph. This downward trend that is fake trend can be a difference between imposing or lifting a lockdown. So what we do with data can actually matter a lot. So, and if you try to explain this nuance or these errors in data to a politician, I think all it's going to end up doing is undermine the trustworthiness of data. Because any slightest doubt in data is going to swing people back to their gut feelings, to making decisions based on what they perceive the situation to be, not on data. And this is the opposite, I think, what we want to do. So can batch be fixed? Well, we could introduce a 1-day delay to the processing, right? But except on weekends, there we need 3 days of delay. And also, what about statutory holidays? There's probably something going to happen there as well. So this is a lot of cognitive load. I think I will make a mistake for sure. You will probably make a mistake. And this is just for one simple data set. Now imagine that you need to join several of such data sets that are updating on completely different cadence and schedule. I think this is just becoming incomprehensible, and honestly, I don't even want to comprehend it because I believe there needs to be a better way to deal with this kind of problems. So what we're learning here is that batch processing is non-temporal. It relies on completeness of data, which is not the case most of the time. Like it pretends that time does not exist and wants you to handle all the temporal problems. It wants to wait for all these problems to disappear before you start processing. So you get all the complexity and edge cases. It's up to you to now resolve them. This makes batch processing very manual. If person walks away from batch processing, even if it's fully automated, it still requires a lot of babysitting. So if person goes away, it's just the data usually stops flowing. The solution to this is called stream processing, and the series of posts from Tyler Akedal in a blog called Streaming 101 is probably the best time investment you can make to learn about this. And the whole idea of it is that data is treated as an unbounded stream of events. This means that processing can run continuously and potentially forever. Because there is no such thing as done state in stream processing as such, the results are emitted throughout as the query continues. So let's look how stream processing is going to work on this messy data that we had. This is how it's going to look like. So not only stream processing somehow magically gets all the results right, there is no redundancy. So we get one result per every single day, and that's it. So exactly what we wanted. And somehow, like through this green line, somehow stream processing knows that it needs to delay the processing for a little bit to get the result right. And this green line is called the watermark. So the watermark is pretty simple concept that tells us that a certain system time, TS, with a very high probability, we have received, the system has observed all events prior to event time TE. So this is what gives us this line on a bitemporal diagram. The watermark can be predictive, so a system might constantly monitor, like, what's the delay between the event time and when I got the event, when the event entered the system, and it might adjust. If it emits too many corrections, that's probably a sign that it needs to bump the watermark. But watermark can also be manual. We can have a fixed offset, but what's more interesting, the watermark might be set by the maintainer of the data set themselves. So a person who enters data in a hospital might indicate to us, hey, I just finished entering all data, like it's Friday afternoon, but I finished entering all data for Thursday. Please go on with your processing. So I think watermark is very beautiful and powerful concept because it shows you the underlyings of what data processing actually is. And data processing really is just a balancing act between correctness and latency. So even in the event of severe event of backfill, like if we lost some data on Friday and only on Tuesday discovered it, stream processing can still handle it and create a correction. What's important, this correction is going to be automatic and explicit. So it's not going to be rewriting the history. It's going to be a separate event saying, hey, remember the data on Friday, I was wrong, it's not 1, it's actually 4. Because it's explicit, it allows the downstream system that consumes this data to actually automate how it reacts to these corrections, which I think is super powerful because it makes stream processing more composable. So it's a widely accepted idea now that stream processing is a complete superset of batch. It's a more complete and intuitive processing model that addresses temporal problems instead of ignoring them. So it handles all the edge cases for you. And it gives you the power to control the trade-off between latency and correctness. If you want more correct data, you just wait more. If you want data to be real-time, you reduce the correctness at the expense of getting more corrections later. And it's more autonomous. Like we can write the query once and run it potentially forever. As long as data keeps coming, the query is going to continue working. There's this misconception, I would say, that stream processing is only used for high frequency data like page views or ad impressions, etc. But I think it's completely false. Like in Commune, we have data pipelines that are built with stream processing and look at the data sets that update only once per year. And we still see a lot of benefit from using stream processing because I don't need to care about all of these edge cases, etc. I know that they're going to be handled automatically for me. So where all of this is going, like in this talk so far, we started with state data and we saw how temporality intruded through change data capture. And later it evolved into domain events, event sourcing, into more event-based form. And we saw that a similar trend has happened in the analytics side, where Snowflake schema gave wave to ELT and data lakes, also becoming immutable, event-based, storing entire history. And now stream processing that has been evolving completely separately for a very long period of time is giving analytics all these interesting tools to process the event-based data faster and more reliably. There's also a lot of interesting parallels and tools like version control system and distributed ledgers that I don't have time to talk about. But I think that the whole space of data is now converging on something that might be called one true data, or at least a much better form of data and the ways of processing data better. So the way I see it personally is that we've spent several decades in this local optima of centralized batch, where processing is very manual, where the latencies are high, data is non-reproducible and unverifiable, and we're slowly crawling out of this local optima. So we've seen that already we're going towards event-based data. This means that it's a no-brainer that we're going to be pushing data towards more real-time, pushing analytics towards real-timeness and low latency. And to achieve that, we need more autonomous data pipelines, and stream processing provides us that. The more complex our data pipelines get, the more important it's going to be for us to understand where every single bit of information came from. So this is where provenance is coming. We need to be sure that the data we're looking at can actually be trusted. The ownership of data is a huge deal. So data is going to remain and actually probably going to become more decentralized, but data needs to be globally integrated. We want data from different sides of the economy to be joined together and processed together. So we're going to be building more interoperable data supply chains. So from my perspective, I spent a lot of time thinking about this, and I saw that if we continue down on this path, and it's going to take us probably a few more decades to reach this new state of data. So I decided to start a project that builds the system, the data management and processing system from ground up in this new state, the state that I think is the future of data. And this project is called Open Data Fabric. It's a protocol, open protocol specification for data exchange and processing. And simply you can think about it as kind of a mix of Git and blockchain for data, or CSV on steroids that has streaming SQL built in it. So you can find this specification on GitHub and contribute to it. Conceptually, here's how it looks like. On the left, we have data publishers that are constantly supplying data to the system. And this data enters this computational graph comprised of derivative data sets. So every blue data set here is just a bit of streaming SQL that continuously processes data. So it enriches it, aggregates it, it extracts some insight, and in real time provides data to decision makers, to AI and machine learning, or for automation. People are completely removed from the system, so they configure these queries, but they never touch data manually. So this is what allows us to reach the real-time speeds, but also creates properties like complete reproducibility, verifiability, and provenance in the system. So really, this is the system that allows you to collaborate on data in a very similar way that you collaborate on software, by collaborating with people to write all these stream processing queries. So ODF dataset, the metadata is actually first-class citizen of any dataset, and we believe that it's actually more important than the data itself, because metadata tells us where data came from and how it was transformed. If we don't know those things, we cannot trust the data, so data becomes useless. Metadata is also a ledger of events, so it contains events like, hey, data was added, or schema was changed, or some processing has happened, or a query was updated, etc. So it creates all these very nice properties, one of them which is zero cost stable references. So you no longer need to version your data, you no longer need to copy data to ensure reproducibility of your data projects. All you need is just this offset in the ledger and you're done. Metadata also allows. Yeah.
Oh, we're down to like 5 minutes. When
Yeah,
we
I
have
just
a
have
question,
one more slide and I'll be done. Yeah.
All right.
Yeah, metadata also enables the evolution of data sets over time. So queries can change and schema can change without destroying all of the downstream graphs that have been built on top of it. So CMU-CLI is the tool. It's our main product that we're building. It's the reference implementation of the ODF protocol. And it's essentially the world's first decentralized data warehouse. It's as simple to use as Git. You can run it on your laptop and start building peer-to-peer data processing pipelines and collaborate on these pipelines with other people. So I believe that this is that simplest way today to try stream processing if you haven't tried it yet, because you can write your queries in Apache Spark and Apache Flink SQL without having to set up these frameworks and without spending weeks on figuring them out and trying to configure them. So I invite you to check it out. You can just look up CMU-CLI on GitHub, and it's going to direct you through all of our tutorial videos. We have a very nice self-serve demo with a bunch of examples. And we also set up a Discord server where you can chat to us about stream processing and data reproducibility in general. And to conclude, I want to highlight that we kind of went for a full circle and we're returning to the core meaning of data. And data is just a record of observations. It's our modern day history book. And you don't modify, version, or diff your history. It doesn't make sense. If you do any of those things, it probably means that you're working with some derivative form or a projection, so which is probably not fit to be your core data model. Data is rarely frozen in time or complete. It flows continuously. So we should stop trying to archive it and build data pipelines instead that are reproducible. We should embrace all the temporal problems and embrace the fact that data processing is a balancing act between latency and correctness, and see that the batch processing hasn't served us so well, that it undermines the trust in data and creates cascade of errors and makes data all way like to them manual. So I think we can do better. We can set a higher bar and revisit how we exchange and process data in order to achieve the reproducibility, provenance, real-timeness. All of these properties are not something that can be bolted onto existing systems, I believe. So I invite everyone to collaborate. I think the next data revolution is not going to come from enterprise, because for decades it's been too focused on pushing things to be bigger, to be faster, but they're not as interesting in provenance and reproducibility. And I think the revolution is going to come from open science and open data communities. So I invite you to work together with us. Thank you very much. I hope it was interesting, and I'm ready to take questions now.
Yeah, definitely. I'm not an expert in your area, but I can still tell you addressed a number of fundamental issues. But anyways, we've got enough time for a couple from Anonymous. Don't you think streaming systems are more vulnerable towards failures and might charge us to lose our data at time?
It really depends how you implement them. Modern streaming systems kind of might store state in the memory, and yes, like they're more susceptible to failures. The way we implement streaming in Open Data Fabric is that we write data as a ledger onto disk, so we persist it. So if stream processing fails, we can always restart it at any previous point in time. So I don't think there is any concern about failures or reliability of those.
All right, and for the second and last question from Sheila, what do you think is the main benefit of removing the humans from the loop?
We cannot simply reach the real-timeness of data without removing people. I see the current world of data as this huge Rube Goldberg machine, where one person takes data, processes it a little bit, exposes it to another person, and this change just goes on and on. So this is, of course, very manual. So if we want, like, take the COVID example, right? It took modern countries, like the first world countries, it took them up to 8 months to build this simple data processing pipeline of just counting daily cases. I think it's absolutely absurd that it took us so long. So clearly something has to change there. I think this manual aspect of data is one of them.
Excellent. Thank you very much for your time.
Thank you very much.
You have a wonderful day.
You too. Bye-bye.